Hi everyone, I am Mukesh from EC department.
I am Arunachalam from ECE department, and our project is a conditional probability based approximate booth multiplier guided by Mrs. Prema, assistant professor of ECE department.
In our project, we have included fixed with booth multipliers, approximate computing, truncation of bits, and conditional probability. To start off with fixed with boot multipliers, a fixed with boot multiplier produces n-bit results for the product of their operands and employs some error correction functions to reduce the approximation error and hardware cost. And they are intensively used in applications, which makes them a good demonstration for approximation of bits. And approximate computing mostly rely on the system or software's ability to tolerate some loss of quality in computed result. And also they provide performance improvements like faster operations and area reduction. So they are mostly used in design of energy efficient digital systems by exploiting the inherent error resilience of applications such as multimedia processing. And by applying fixed with booth multipliers, we can gain improvements in circuit performance like improved speed, power, and area and cost reduction actually. And by applying approximate computing, the outdoor expenses and power dissipation is very much reduced while maintaining a decent output quality. And in the approximate computing, we apply a probability analysis on partial products, and the probability applied here is conditional probability, and we discuss it in the later part. Our proposed system is by applying a truncation to the partial products generated by multiplier bits. Actually, in the truncation of minor part, we can apply conditional probability to improve the accuracy even while maintaining reduced cost, reduced hardware requirements. We can get a proper output. And in the block diagram, we can see a booth encoding part where the multiplier bits are fed in, and the output is obtained as a 4-bit output. While giving a 8-bit input, we can obtain a 4-bit as output for booth encoding. And in the partial product generation, 8-bit multiplicand and the encoded 4-bit multiplier is multiplied to get the partial products, and they are separated into an accurate part and truncation part. And in the truncation part, we further divided them into major truncation part and minor truncation part. And actually in the minor truncation part, we apply the conditional probability to get the output, and actually finally combine them to get the final output.
We have the partial products of the multiplicand as well as the multiplier. The output of the multiplicand and multiplier is 16 bits. We are going to separate 16 bits into two parts, truncation part as well as accurate part. We are going to separate the truncation part into two types, which is TP major and TP minor. This is the MLCP algorithm. These are the formulas we are going to use, which is S1 is equal to beta plus 3 1 bits whole divided by 2, where beta is equal to summation of Zi. Here Zi is the encoded multiplier. Post truncation. Post truncation is nothing but we are going to generate the partial products and we are going to add into a 16-bit value. After addition, we are going to discard the LSBs. So here we are going to get the MSB as the output. In pre-truncation, we are going to get the MSBs by discarding the LSBs before addition. This is the comparison of the results. From this table, we are referring that by applying the MLCP value to the pre-truncation part, we can able to get the approximate value by reducing the area, power and time. Here is the hardware and softwares used, which is FPGA, Model Sim and Xilinx.